Okay, hi everyone. My name's Angus. I'm a PhD student here at the University of Nottingham, and today I'm going to be showing you all how to make a triaxial sample for testing soils. For those of you that are on the Geotechnical Modelling course here at the university in fourth year civil engineering, Master Civil Engineering, congratulations for taking one of the best modules I think that the department offer. I was a student in your year, I think 2 years ago now, and I did this type of experiment in the lab with Dr Heron, and I think it provides a really good background to some of the work that you do, the theoretical work that you do with Professor McDowell, and really sort of cements your understanding of certain things, certain ways that you do stuff in your theoretical work, and all around it just gives some really nice context as to why we do the work that we do, why some of the stuff we learn is important. So without further ado, let's look at making a sample. So first things first, we need to check we have all of our items present, and we'll walk you through stuff as we go now. Here we have our triaxial cell. This is a cell for 38mm samples, 38mm being the diameter of each sample, and it can test up to, on the controllers, up to 1000 kPa effective stress. So let's take off the top half of the cell, because we will need that later. This is the bottom half of the cell. This is the sort of the business end, as it were, with all the valves on it that control the flow of water in and out of the cell. We have valves for the cell pressure. There we have the pore water pressure valve, the top cap valve. We have on this side, I think that's another cell pressure valve, and this is the back pressure valve for the bottom half of the sample. We will be using double drainage, so we have a top cap on this platen with an associated valve. Here we have the pore water pressure transducer, the PPT, pore pressure transducer, that detects the change in some of the change in pore pressure in the sample whilst it's on the whilst it's inside the cell and being tested. Obviously you can't test the pore pressures sort of invasively, as it were, otherwise you'll disturb your sample. So we have this to detect our pore water pressure changes during various phases of testing. Here we have some de-aired water that's crucial for saturating the lines to our sample, to make sure that there's no air bubbles going in, to make the pressure changes as plastic as possible and remove any air from those lines. We have O-rings here. We've got two on this membrane spreader, which we will get to shortly. We have two on this spacer that will help us put O-rings around the top half of our sample. We have in this bag membranes. These are 38mm membranes. We keep them in plastic bags so that they're not harmed by UV light. In the teaching lab here, we have windows allowing natural light to get in. Inside the geotechnical lab next door, there is, all the blinds are shut to make sure that the UV rays from the sun can't disturb and break down the membranes, which they will break down over sort of a fairly long period left in the sun. So that's why we keep them in a black plastic bag. They're also kept in a drawer inside the geotechnical lab. Here we have some 38mm filter papers that are used to give a good seal and make sure that our soil sample isn't moving through any of these lines. We only want water flowing through these lines. We want to make sure that the soil is confined to our sample and membrane. Here we have some silicone grease that's used for sealing parts of our triaxial cell. I've got some pore stones here that again are used to filter out any soil. They're used as sort of the last line of defense for soil, and they've been saturating there in some water for a day now, just to make sure there's no air left inside them. I have one rubber band. These are optional, but I find them quite useful for controlling the, or making sure that our top cap feed line doesn't disturb the loading ram as it's shearing, but we'll get to that soon enough. And the most crucial thing in triaxial testing is our soil sample. So here we have a sample of, I think this is Sheffield soil, as the name suggests, taken somewhere in Sheffield. And this stuff is quite stiff and quite handy to demonstrate making these samples, because they can get quite fiddly. Yesterday we made samples using a mix of 50% kaolin clay and 50% of a sandy silt, and those samples went on the Triaxial rigs next door, and we'll show you them at the end of the video, just to give you an idea of the final product when it's all assembled. The sample that we use for that, this kaolin silty sand mix, was although we consolidated it to around 50 kilopascals, it's still quite soft, and so we had, myself and one of the lab technicians, Andy Madison, we used two sets of hands to create the sample, because when you're spreading membranes, they can be quite fiddly, and you don't want to disturb your sample, so two sets of hands can often help. Okay, so let's look at getting going then. So the first thing I like to do is stretch the membrane around this metal tube here. Is one thing that is often forgotten. The last thing really that you want to do before you disturb your sample is take it out of the plastic wrap. The plastic wrap there is used around the sample, is used to make sure that the water content doesn't change and the sample doesn't dry out. So we keep them in plastic wrap before we assemble them and saturate them, just to make sure that the water content doesn't change. Okay, let's try and get this membrane in. So I'm going to drop the membrane through this metal tube. I'm going to make sure I've got sort of an even distribution at both sides, and I'm going to fold the membrane back over itself. It's a good job we are flushing these out now so we don't damage the PPC, and we have a nice blob of de-aired water flowing through there, and you can see all the air bubbles flowing up to the top, so that's good. We can make that nice, and here I will shut off the valve on this end so that we don't pressurize the PPT. These are very sensitive bits of equipment, they're also quite expensive, so we want to make sure always when we're using the PPT and changing valves next to the PPT that the pressures don't change in them, or we change the pressures exactly how we want and we don't incur any other effects. So I'll close off this valve now, and I can take this pipe out. That's good. So now we have one half of the lower platen fully saturated, and we can look to saturate the other half here. So I will turn the lower platen around, and we see here on this valve, the valve pointing towards me, indicating it's open. I'm going to squirt some more water in, and you'll see some air bubbles come out of the top. Just there, keep pushing it. And there we have the other side of the lower platen fully saturated also as water starts to come out. So I'm going to turn this valve so that the water is always trapped in there and there's no air bubbles left inside there now. So the bottom platen is fully saturated, which is good. So now let me get my sheet of tasks back up. It's always handy to have this just for reference. So next on our list, after we've saturated the lines with water, we want to grease the lower cell. We use this silicone grease around, we put it around this O-ring on the bottom part of the cell, which will interface with this ring here. We use silicone grease here, the sort of the oliphobic silicone grease, to make sure that under high pressures, none of the water starts to spurt out the side. So we're going to liberally apply some silicone grease all the way around. Nice blob of it, and spread it around the bottom of our cell so that we have a good barrier against water. You can pressurize these cells, as I said, up to 1000 kPa, and under those sort of pressures you want to make sure that you haven't got any water leaking from anywhere, as well, your test will fail at that point, and all this work you'll have done would be pointless. So we've got a good line of grease there. I'm happy with that. Okay, so next job on the list is to cut our sample to length. So here we will take our sample. You know what we don't have? A ruler. I will be right back in about 20 seconds. We are back. I've got my ruler here, so we can mark out the length of our sample. Now when we are triaxial testing, the length of our sample, and this I think is contained within the standards for triaxial testing, the length of our sample should be twice the diameter of the sample being 38 millimeters in diameter. So of course we want 76 mil of sample in height. So what we'll do here, this sample sort of reflects something that might have come out of the ground. It's not sort of flat on either end. So what we'll look to do is just shave one side off so it's nice and flat, and then we'll work from there down 76 mil to make sure we've got a nice flat cylindrical sample. So let's make a cut here. Being quite a stiff sample, this is quite easy to work with. This is just a metal wire, no serrations on this. What we use to get a nice top of the sample there. Shave off that. Oh, it is quite stiff. Let's shave that bit off as well. Okay, well, the good job is this is for demonstration purposes only. Being quite stiff, it's also seems to be quite brittle, but we'll work with what we've got in proper triaxial testing. This sample isn't actually going to be tested. This is just for sort of demonstration purposes. This sort of reassembly of your sample wouldn't take place. This sort of resembles Play-Doh in that sense. You can sort of just mash it back together and it sort of looks okay. There's a few cracks in this sample as well, where there's obviously air bubbles inside. When it's been cored, it's not been quite cored incorrectly. It's been cored incorrectly, but we will plow on anyway. So we have one end of our sample. We will measure up from that 76 millimeters. So I'll make a slight impression on my sample there to make sure I've got my line, and then again we'll trim off the end nice and easy. Little by little this will come off. Let's try and not damage the end of this side. Oh dear, that's not straight. It's happened again. God damn it. Okay, well, it's close enough. As I say, this one isn't being tested. But the point remains, you should always make sure that your sample is nice and cylindrical. See, from that angle, that doesn't look too bad. We're happy with that. We can move on. Okay, so now we've got our sample cut to the correct length. We need to put our pour stones and our filter papers on top of our bottom platen. So I'm going to take one of these pour stones. Pour stones go on first in this. Pour stone goes on there, and we're just going to saturate it a bit further with some of this de-aired water. Get a nice layer on top. And then we take one filter paper and lie that over the top of our pour stone so that they all line up. Nice. And just add a few drops of water on the top there. Next, we add our sample to the top, making sure it lines up all around. And then the next job is to seal the membrane around the sample and pop the O-rings on the bottom. When we place our O-rings, we don't want to disturb the lower half of our sample. So we need to keep the O-rings away from the pour stone, the filter paper, and the bottom of the sample. Returning to our membrane extruder before, let's put the vacuum back on. You can see there it's nice and tight around the inside. And as I offer this over the sample, you can see it sort of goes all the way around and it doesn't interfere with the sample at all. If this was a very soft sample, you want to make sure that you aren't, your membrane isn't coming into contact with your sample until exactly when you want it to. So I will remove the vacuum now, and you see there the membrane has got quite a nice tight fit over the sample. I'm going to remove the vacuum pump. And now the job is to slide the membrane down over the bottom of the platen here. So if I get a nice pick up on the membrane, making sure to be careful. Again, if this was a soft sample, we want to be disturbing it the minimum amount we can get away with. I'm going to slide the top part of the membrane up as well to release the spreader. There we go. And now the spreader comes away. So now I have the bottom part of my platen with the membrane overlapping down there, and you can see on the platen as well, there's quite a lot of room there for the two O-rings to snap in. You always want your O-rings to create quite a good seal around this to make sure that there's only one way the water can travel out of the sample, and that's through the pour stones and the filter papers and out through the valves. So when we pop the O-rings down, we want it to be just on one course of membrane rather than overlapping on two. So I can take the O-rings now and just easily roll them down and snap them into place on the platen there. So that's one, and then we'll pop the other one down. And there we have a good nice seal around the bottom of our sample, and it's starting to come together. I'm sure you'll agree. So we have the platen, which is connected to the back pressure valve, which is the one on this side of our sample, and also the pour pressure transducer, it's connected underneath there. And we have a good nice seal with the O-rings and the membrane going through, and those valves connected through the pour stone, through the filter paper to our sample. Okay, so Next item on the list is to seal the top cap or add filter papers and pour stone to the top of our sample now. So likewise we did for the bottom, we need to pop a filter paper and pour stone onto the top of our sample. So I'm going to take this filter paper, fold it just ever so slightly so it can fit into the top of the membrane. Again, being nice and delicate with our sample if we can. And that filter just sits nicely on the top of our sample there. And I will saturate that with a drop of de-aired water. And then, much like if you were applying a screen protector to your phone, you want to push the air bubbles out of this top. So I'm going to slightly manipulate the filter paper to get a nice seal to push all the air bubbles out, so that we have a nice saturated top of the sample. I think that looks pretty good. The air bubbles out of there. The next job to do is to put the pour stone in. Again, this, especially if this was a soft sample, what we had to do yesterday when we were making them with the clay sand silt mix. Andy, the technician, prized open the membrane at the top, carefully keeping the sample steady so that we could just pop the pour stone down. With a sample like this, it's quite easy to do. Sometimes, if your sample is especially stiff, you can roll the membrane back over itself temporarily whilst you pop the pour stone into place. So I'm gonna just grab the exterior of the membrane there and lightly push down, pour stone into place. Nice and easy, so that we've got a good seal. Again, nice, and you can see the water there that we applied to the filter paper starting to come back into our through the pour stone there, so that's nice. I think you can see it just there if I check my camera. Nice. Okay, so the next job to do is to seal the top cap around the sample and with the membrane and the O-rings. And I'm going to apply a nice layer of silicone grease around just on the top cap, the exterior of the top cap as well. Just to add that extra barrier to stop water flowing out around here. This silicone grease is used quite a lot in triaxial testing and all sorts of soil testing. I use it in some of my work as well. Okay. And also, before we forget, we need to saturate the top line, just like we did for the bottom lines for the pore pressure transducer and the back pressure valve for the bottom of the sample. We need to saturate the top line as well. So we will do that now by taking some more de-aired water out. That should be enough. And with the valve open again, we're just gonna place some water inside, and you can see it's starting to rush through the line there, and you can see all the air bubbles rush out. That's good. We want to make sure that we don't have any air bubbles in this line if at all possible. So after pushing that through, I'm going to hold the line with my finger over the top, and I'm going to turn the valve at this end to make sure the head can't change, and that line is fully saturated with water now. On a lot of triaxial tests, often it's quite difficult to make sure that this line is fully saturated, but just remember your sort of elementary hydraulics and keep your finger over one half of the line, and you make sure that the water doesn't get any air inside it. So now we have a fully saturated top line as well. We can seal this line to the top of our sample. So I'm going to take this O-ring spacer and with the O-rings attached, and I'm going to just offer it through the tube. You have to do this in this order, otherwise you can't fit the O-rings around your top cap once the membrane is sealed around it. And I'm going to make sure that my feed line for the top cap is nice and straight and not around my sample. We want this to be outside of the center line of the sample so that the shearing ram doesn't disturb the top of the sample when it moves down and doesn't hit this feed line. If this was a soft sample like yesterday, when this line is knocked by the shearing cap, it can often knock the sample offline and you'll get some odd shearing behavior. I think we had that last year with some of the students who took this module, where the samples weren't quite on the money. So I'm going to push this down into the membrane. Again, you would be quite delicate with this, but just for demonstration purposes, let's show you a bit quicker. With it being a two-man job, it's certainly easier for this. But there we go. We have our top cap pressed down onto our pour stone. So there, if we just check our layers again, we have likewise on the bottom, we have our top cap, our pour stone, and our filter paper, followed by our sample there. So now we have, we can do double drainage, and this will speed up the consolidation of our sample and our saturation of the sample, which we had to do. These videos being produced fairly quickly. We didn't have much time to prepare this year for, well, the reason everyone's using at the moment. And so we are trying to saturate these as quick as possible. So double drainage is certainly a must. Okay, now, so I'm going to fold my membrane back over the sample and the top cap there. Making sure, again, it's not bunched up. Or actually, what we'll do first is we will put our O-rings on, just to make sure that they are sealed around one, like on the bottom side, that they're sealed around one cap or one line of membrane. So taking our O-rings, make a good seal, snap them into place, keep them nice and straight. Again, this sample, where I've cut it there, you can tell even the small margins make a difference in triaxial testing. You can see how the top cap isn't sitting perfectly level. That's because of where I've cut the sample and it's not perfectly straight. So those types of things you really do need to pay quite a lot of attention to, but luckily we aren't testing this one. So we'll snap that O-ring onto place, and there we can remove the spacer with its handy gap in the side, and we can just flip the membrane back over the O-rings, ensuring we've got a good seal around. And also, of course, making sure that the membrane itself isn't overlapping the sample twice. Part of the standards when you're accounting for, or when you're calculating your shearing or your effective or your deviatoric stress, sorry, you need to account for membrane correction factors. This membrane, even though we haven't got it in a cell, is compressing our sample ever so slightly. It's exerting some pressure on our sample, and that's one thing you need to account for. And so you want to make sure that your sample isn't overlapped by 2 courses of membrane. So there, I'm just going around and making sure that the membrane, we can flip it over itself again on the O-rings, just making sure that the O-rings and the membrane are only touching the top cap. And I think we look good there. Okay, so the next thing I like to do is secure this back pressure line to the top cap. One thing that often happens when you insert it, when you try to put the top half of the cell over, because this line, I'm sure you can see there, sits outside of this O-ring, it can disturb the sample when you put the O-ring on. If I was to just show you there, you can see how that starts to lean as I push this very light pipe, and you can see the sample starts to lean in a way that isn't good for triaxial testing. We want everything to be in a line, and so that our effective stresses, our principal stresses, are operating in the right manner with our cell and our the load ram the sigma 1 and sigma 3. So I take this this rubber band and I give it a quick double knot, and then we can just pop it over the top of this pipe just to make sure it's nice and close to our sample, not disturbing it. So that's all nicely in a line there, aside from our sample not being cut to the right, not being cut perpendicular, and that will stay out the way of the loading ram as it falls over our sample. So that's good. We want that to be out the way and won't disturb our sample there. So after that, we have our line saturated, we have our sample on, we have good seals around our O-rings and our membrane. So this sample is almost ready to go. If it was going to be tested, we would, after putting the cell on, nice and carefully, making sure not to disturb our sample, and sealing it up with these thumb screws. You can see there part of the issue. So that load ram is has actually fallen onto our sample. So perhaps when I put on this rubber band, I didn't quite do it in the right way. It really depends on how you orient the top cap versus the back pressure line for the top half of the sample, and making sure that you keep that out of the way. I can show you on the samples we did yesterday in the other room that this line often causes an issue, and maybe I put it on slightly incorrectly. Perhaps if we just give it one line. One, give it a nice double that there. And we offer this over again. When the load ram comes down, you'll see it will disturb the sample. So that's not very good. That's no bueno. But that's the general principle of building a triaxial sample. And once you've got that done, you can go and do some triaxial testing. If you flood the cell with water, you can control the cell pressure, and now you've got full control of the back pressure, both at the top of the sample and at the bottom of the sample, and you know your pore water pressures for during shearing. So that is how you assemble a triaxial sample, aside from the little error we have with the top cap there. But now if I take you into the lab, we can have a look at some of the samples we put on yesterday. So let's go into there. Okay, so back into the geotechnical lab now, and this is one of the samples we set up yesterday. You can see there how we've applied the rubber band to keep the shearing rod outside of the top cap pipe there. We've got a good seal around our sample with the membrane only on the top cap there. The O-ring sat underneath that. Likewise at the bottom, you can see that. This sample is saturating at the moment to make sure that we get as near as we can to 100% saturation of the sample. It's currently at an effective pressure of 30 kilopascals. When we made these samples, we took them to around 50 kilopascals of consolidation stress. So we're saturating below that level now, so that we are ready to consolidate. We first of all need to do a B check, which will be shown next time on one of these videos, to check our saturation level of our sample, and then we can look at consolidating our sample and then shearing it so that we can work out some of our material properties and see how they fit with the theoretical framework and the experimental or the quasi-experimental method that you're being provided data for a pure kaolin cell. And also you can reference that against the numerical work that you'll be doing with Dr. Marshall if you are on the Geotechnical Modelling course. So that's all we have this time. Hope it's been informative and you've started to learn a bit more about the samples and the actual specifics of what you're learning in class. And I will see you in the next one, I suppose.